So we've found a few integrals, and in the past lesson, what all of our integrals had in common was that they were convenient shapes, right? So they ended up being nice geometric shapes that we could divide them up easily in. Now, notice, if we take a look at our function here, f, not so convenient, right? So it's kind of triangular, but notice it doesn't actually ever touch the x-axis even. And I guess, so we're looking at from 0 to 3. So from 0 to 3 would be here. So that's a little bit more convenient. But even still, if I want to find this area, I get all these curvy shapes that are really hard to describe. Right? So obviously this problem of integration of finding this area underneath the curve is a little bit more challenging when the function is more complicated, right? We are going to begin our study of integrals by estimating them. So we're going to approximate this integral from 0 to 3. Okay? So this says if 3 subintervals of equal length are used, 3 subintervals of equal length. Well, what that just means is we're chopping this up into 3 pieces, and we're going to draw rectangles to make a guess at what this area is. So let me show you what that looks like. So first of all, it's going to ask you for the width of each subinterval. Well, we have the integral from 0 to 3, so 3 minus 0 is 3, right? We're going to divide that by 3 intervals. So you're always going to do this to figure out how many intervals to do. In this case, it just comes out to be 1, right? So the width of each subinterval is going to be 1. What that means is our rectangle is going to be 1 unit wide. Okay? This problem asks you for a midpoint Riemann sum. Midpoint Riemann sum. So what that means is it means that the middle of each rectangle is going to be on the function. So let's take a look at what this looks like, okay? Okay. So here are my 3 rectangles. Notice they each are width 1. And then what I did is I dragged them so that that middle point is on the function. So this is the midpoint, and it's a midpoint Riemann sum. The reason I'm making a big deal about this is because there are different types of Riemann sums, and we're going to see others in the future here. So what I could do, right, is I could measure each one of these rectangles, find their area, and add them up, and that would be an approximation for this integral, right? Now, what we know it's an approximation because we have these areas that I'm going to highlight in yellow that are under the function but are not included. We actually have these areas that are not under the function but we did include, right? So this is an approximation, right? And these are like errors in our estimate, in our approximation. Okay. So our actual integral, it's a little bit different from this, right? Now, the reason this is so important to understand how to approximate these is what we will do is we will use this idea of limits in a future lesson to investigate what happens when we make this rectangle very small. And what we'll see is as these rectangles get smaller and smaller, our approximation is better and better. Okay, so that was our midpoint Riemann sum. We're going to look at what left and right Riemann sums look at here in a second. Same thing, they're ways of estimating integrals. But they tend to be more or less accurate, or like over or estimate or underestimate integrals in predictable ways. So let's take a look at what those look like. Here we have a right Riemann sum. Okay, so you'll have to read the text to figure out which we're drawing. A right Riemann sum approximation of the integral from 0 to 2 of f of x dx. Okay, so that's from 0 to 2. So we want this area underneath the curve. And we're going to use 5 subintervals of equal length. Okay, so the width of each subinterval, well, 2 minus 0 over 5. So those are the bounds again over 5 intervals. Well, it's going to be 2 over 5, which is going to be 0.4 we put in here. And then I'll show you what our right Riemann sum should look like. So here's our right Riemann sum. And notice it's a right Riemann sum. The right-hand side, the right corner of each rectangle, is the part of the rectangle that is on the function. Okay. So that's really important to capture in your notes, because if you get these wrong, this is going to be why. So the right corner is on the function. The right corner is on the function for right Riemann sum. Okay. Now, the point of this lesson is to figure out whether these approximations are over or under approximations. Well, in this case, we have an over approximation. And here's why, right? So we have all these corners of the rectangle that are sticking out. Okay. So this is an over approximation of the integral because it includes these little corners in our total. Okay, so this is an over approximation. And notice the delta math will ask you if the function is increasing or decreasing. So this is an over approximation because the function is increasing. Meaning, if let's draw a quick sketch. I should not put it there though, because that's unclear. Let's draw a quick sketch of the opposite case. So an under approximation for a right Riemann sum. So if I draw a decreasing function and I put the right corner on the function, notice I suddenly have an under approximation. Right? So right Riemann sums are over approximation when the function is increasing, and under approximations when the function is decreasing. Okay, we'll do one more example this time. You probably guessed it, of a left Riemann sum. Okay, here we want the integral from 2 to 8 of f with a left Riemann sum using 3 subintervals. Okay, so that means we have 8 minus 2 over 6, oh, just kidding, over 3, right? And that gives us 8 minus 2 is 6 divided by 3 is a width of 2. Okay, so here is the result. So we have a left Riemann sum here. The left corner is on the function. And notice this is an under approximation. But I could draw the opposite case, where I have a downward sloping function, a decreasing function, and I have the left side of my rectangle on the function. These rectangles are a little crooked, but and notice it would be an over approximation this time. Okay. So whether these estimates are appropriate or not depends on whether the function is increasing or decreasing. That is the true takeaway from this lesson. So the point of this lesson is to sort of investigate and internalize that relationship.